We'll now talk about architecture choices. So this will be divided into three parts. First, the choice of the measurements location, then the choice of the measurements transmission protocols, and the last, the infrastructure that we'll use for the system. So first we have to think about what the system components will be. So first we have Wi-Fi access points which provide access to the network and may also provide other features such as measurements, mesh networking, and so on. Then we will use mobile devices which will move inside the network, use some services, and due to those services they will need to be located. And last, we'll have need of a positioning server which will compute the mobile devices locations and communicate with the other components, either to get the proper data to compute the device locations or to provide the device locations to the services which require this location. So we'll have several choices to make when designing the system. In terms of infrastructure, we can use a wired network, a mesh network, or other kind of infrastructure. This infrastructure will impact on the protocol we use. Then we can choose to perform the measurements either on the access points or on the mobile device. So if we use access points, it also impacts the protocols we use. And we may choose between a centralized or a distributed system, which also impacts on the protocol we use. So let's consider mobile device side measurements, which means that the measurements of the RSSI values are performed on the mobile device itself. So this has all of the shortcomings that I presented in the introduction of the indoor positioning systems. So the problem that you cannot develop RSSI measurements on each kind of device, and there are a lot of devices, hardware and operating systems that have to be tackled. So it's a huge work, except in special situations where you provide the devices to the people who use it. But this is the most simple case in which you perform the RSSI. You get all the samples for your device and you send these samples to the positioning server. Then, and this is what we'll be doing in lab work, we can use access point side measurements. So that means that on the access point we develop a sniffing tool to get the RSSI values for all of the frames that go in the air near the access point. The access point then communicates with the positioning server. So it's a bit more complicated because it's a distributed RSSI measurement system with no global clock between the access points and the server, but it's an efficient choice. So since it's a distributed system, we have new problems, which are first to get a global knowledge of the RSSI samples from the server's point of view. So each access point gets only a part of the RSSI samples, which are the samples that is linked to itself. And all of these samples have to be sent to the servers and aggregated within the same time. Then we have the trade-off between the communications and the amount of information. So we want as many information as possible to improve the accuracy of the algorithm, but we don't want to collapse the network with its own services by sending a lot of samples from the access points to the positioning server, which would be counterproductive for the system. So that's why I will propose you several protocols to aggregate the samples from all of the access points. So first is the raw RSSI sample transmission, which simply means that each frame received from a mobile device is measured by each access point within range and then sent to the server. Of course, it consumes a huge amount of bandwidth, since one frame, real frame in the network, which corresponds to an actual service, will trigger another frame between the access point and the positioning server. It can only be considered when all the access points are wired to the server's network, because if they are communicating with the server through Wi-Fi, each frame of the access point will also trigger another frame of measurements, and then you have an infinite loop and your network goes down. And even with a wired network, it's usually not an acceptable solution. In this kind of system, the server will use the last samples to locate the device. So it will have a sliding window on 1 second and use all samples related to a device on the last 1 second to locate it. Then we have another solution, which is the periodical grouped RSSI transmission. It's based on gathering data based on a time window. So here we have the mobile device. It requests a service, it sends some data, and all the access points within range will record the RSSI and store them in their memory. Then after a time, they pack everything in a request to the server, and they send that to the server. And when the device makes a location request, which is recorded by the access points, the server uses all those data here to respond to the mobile with its location. So the problem is that it will generate a lot of traffic with many devices if only a part of them want to be located. Then we have the on-demand RSSI request. So when receiving a location request from the device, which will be recorded by the access points, the server will ask for the RSSI for this mobile device to all of the access points, which will in turn respond with their values. And then the server will send the location. It avoids sending useless RSI samples to the server, but it will add the server requests to the access points to the traffic. So it might be a good choice when only a very small part of the mobile devices want to be located, but not if there are a lot of devices which want to be located. So another solution is to use a trade-off between the on-demand and the grouped transmission. So the both previous solutions I proposed, in which on its first location request, the device sends its request to the server. It's recorded by the access points. So the server will ask the access points to survey the frames for the mobile device M. So it means starting from now, you record the RSSI for M and you send them to me periodically. So at each window end, so here for instance, all the RSSIs for the surveyed mobiles are sent to the server, which use that information to respond the location to the mobile device. So this way you only have to transmit a group of RSSI samples only for the surveyed mobile devices, which are the ones which want to be located. So it's one of the most optimal protocol that we can use. Sometimes we have to mitigate the lack of traffic between the device and the infrastructure when the user device is not requiring other services than being located. Indeed, with few RSI values to be measured and forwarded to the server, the accuracy might be poor. So from the server side, you have to keep track of the number of the device transmissions, so based on how many samples you received, and you may ask the access points to trigger dummy traffic from the device, for instance by requiring layer 2 acknowledgements based on the Wi-Fi protocol stack. This way you can get more RSI samples and improve the accuracy of the positioning. Let's talk now about the infrastructure choice, which is the physical architecture of the network. So the most common Wi-Fi infrastructure is the fully wired access points infrastructure. That's what we have with a drone, for example. So we have a core network here with our positioning server, some switching environment, and on the switches you have the access points which are connected with Ethernet cables usually and have a direct access to the core network, and your device is connected to the access points and it can bridge its packets through the core networks to its services. With this kind of infrastructure you cannot have thousands of access points because you require to cable every access point, which takes some place and requires a lot of work. Then you can use a mesh network, so you have the core network part. One or a small number of access points are connected to the wired network, and then you have other access points which are only connected through virtual radio links going back to one of the routes which are connected to the wired network, and you build this spanning tree of virtual radio link through a dedicated protocol, and your phones connect either to a root access point or one of the mesh network, and they see it's transparent from the device points of view. Then we can use repeater mode access points. So for instance, if we have the core wired network here and some of the areas have poor coverage, you can extend with only one radio link from the wired network to another access point, which is a repeater, and which improves the coverage of the network. And again, your device will connect to any of the access points. It's transparent from its point of view. Then we could use a combination of mesh network and repeaters. So we have the core wire network. We have the mesh network with its spanning tree of virtual links. And for the last hop in the network, you can put a simple repeater radio link to increase the coverage of the network. It's useful especially when not all the access points will support mesh networking, because repeater mode is something that every access point is capable of. Then the last solution, which is not really about the infrastructure from the device point of view and the operations point of view, is dedicated for Wi-Fi positioning. It's to use access points or any other lightweight device as a network client to provide RSSI samples probes inside the network. So here is the network infrastructure, the device that we want to locate, and here are our probes, which are connected to the access points through a client connection, exactly like the mobile device. And they can measure the RSSIs from the device and then send this information through their client connection. It's better if they use the different frequency band than the device. So for instance, 2.4 GHz for the devices and 5 GHz for the client connection of the probes. It's a good choice. And it will be sensitive to the amount of messages generated by the RSSI transmission protocols, because here is a bottleneck in the network, since it's limited to the Wi-Fi bandwidth, which is less than the wired network.